Assalamualaikum, my name is Najaf and my roll number is 21TE06. The lab of Dsp that is under discussion today is lab number 3 and its title is Representation of Unit Impulse, Unit Step and Exponentials Making Signals Out Deltas. The lab objectives are representation of unit impulse function and unit step function, making unit step function using unit impulse sequence, and making any arbitrary signal out of deltas. Task number 1. In task number 1, we have been given a code snippet, also with a few lines that we have to run in the command window. The function that we used in this code is of impulse sequence. So when we will run this code in MATLAB, we will observe an impulse sequence in the output. When we enter the given lines in the command window, we will observe an impulse sequence. And in impulse function, we observe that we only get the signal at 0 and otherwise the values are 0 for the rest of the range. Now we were asked to observe the following aspects. Shift the unit impulse to right, shift the unit impulse to left, and multiply the sequence with scalar value and see the effect. So here n0 is the shift amount, n1 is the lower bound of the range, and n2 is the upper bound of the range. Whereas for generating the impulse sequence, we created an array n containing integers from n1 to n2 inclusive. This defines the range of indices. Here in this line, x is equals to n minus n naught equals to 0 defines that it generates an impulse sequence x where it is 1 where n minus n naught equals to 0, otherwise it is 0 for other values. To shift the impulse to the right, we have used this term and it shifts the range of indices by n naught units to the right. This is done to match the desired shifting behaviors. So when we run this code, we observe that the impulse sequence was initially centered at n is equals to 0. Since n naught is set to 2, the impulse sequence is shifted to 2 units to the right. And the plot will show a spike at n is equals to 2, indicating that the shifted position of the impulse. The rest of the plot will be 0 since this is an impulse function. Now for shifting the unit impulse to the left. Here the code will be same that was for the unit impulse shift to the right, but the only difference is that for right shifting we had n minus n naught, but for left shift we'll have n plus n naught. So when we'll run this code, we'll observe that the unit impulse function has been shifted to the left. Multiplying a scalar with the unit impulse function, the only difference is in this term, which explains that it multiplies the impulse sequence x by the scalar value scalar, and this scales the amplitude of the impulse sequence. So when we run this code, we will observe that the original signal was at the amplitude 1, but when we multiplied the unit impulse function with the scalar value, which was 2, it shifted to the amplitude 2. Task number 2. In task number 2, we have been given the code snippet for the unit step function, where the function that we used is of the name step sequence. And when we run this code with these 3 lines in the command window, we will observe a step sequence in the output graph. When we enter the lines in the command window, we will observe a step sequence in which the step sequence says that we have values less than 0 equals to 0, and for greater than 0 we have at the amplitude 1 till infinity. Now for the observations, we were asked to shift the unit step sequence to the right, to shift the unit step sequence to the left, and to multiply the sequence with the scalar value and see the effect. So here n2 is the shift amount, n1 is the lower bound of the range, and n2 is the upper bound of the range. For generating the unit step function, we have defined the range of the indices, and this line here will generate the unit step sequence. We made a function with the name n shifted, and n minus is equals to n minus n naught, which shifts the range of indices of the unit step sequence by n naught units to the right. So when we run this code, we will observe, we will see that the unit step function has been shifted to the right. Now to observe the shift of the unit step sequence to the left, the code will be same that was for the right shift. The only difference here is n plus n naught, which was n minus n naught in the right shift case. So when we will run this code, we will see that the graph has been shifted, the unit step sequence has been shifted to the left. Now observing the multiply the sequence with scalar value and analyzing the effect. Here we have defined a term, a scalar term, or you can say a scalar value, that is 2, and the function xn scaled is equals to scalar multiplied by x of n will scale the amplitude of the function to 2 vectors. So now if we run this code, we will observe that in the original unit step sequence, the amplitude was 1, but when we multiplied the sequence with a scaling factor which was 2, we observed that the amplitude has changed from 1 to 2. Number 3. Unit step sequence can be constructed by add shifted impulse sequence using this formula. We've been asked to use unit impulse sequence of task number 1 and construct unit step sequence. The question is it possible to construct the shifted version of unit step sequence by summation of deltas? If yes, then what is required to do so? Secondly, we've been asked to use commands pause, hold on, and hold off in our code. N1 is the lower bound of the range of indices, N2, that is 5, is the upper bound of the range of indices, N is the array containing integers from N1 to N2 defining the range of indices. For initialization, U is initialized as an array of zeros with the same size as N, and this will hold the unit step sequence. Here we have used a loop, and the loop will iterate from k is equals to 0 to length n minus 1. Inside of the loop, we have used the impulse sequence function, which is called to generate the impulse sequence x at index k. The impulse sequence k is added to the unit step u, and the impulse sequence x is plotted with stem, and there is a pause of 0.25. We have used the term pause. and the pause is of 0.25 to visualize each step of the construction. And then we have just plotted the graph. We have also used the term hold off. Now, if we run the code, we saw that the first subplot shows the individual impulse sequences being added to construct the unit step sequence. Each impulse sequence starts at an index corresponding to k and has a height of 1. The second subplot shows that the final unit step sequence, which is the cumulative sum of the impulse sequences, it starts from 0 and gradually increases to 1 as more impulse sequences are added. The axis -5, 15, minus 0.5, 1.5 command that we used here in the code sets the limit of the axis to -5 to 15 and the y-axis to -0.5 to 1.5 for better visualization. So the question that was, is it possible to construct the shifted version of unit step sequence by summation of deltas? The answer is yes, it is possible to construct the shifted version of the unit step sequence by summation of deltas. And in order to do so, we would need to adjust the starting point of the summation. For example, if we want to shift the unit step sequence to the right, we would start the summation from a negative index instead of 0. Similarly, if we want to shift it to the left, we would start the summation from a positive index. Number 4. Any arbitrary signal can be represented by unit impulse sequence that is given by the formula. Use unit impulse sequence of task number 1 and construct the following signals. Bolded number is at 0. So the given formula states that any arbitrary signal can be represented by summing up scaled and shifted unit impulse sequences. And each term in the summation represents the value of signal x of n at a particular index n. And we have been given the formula. Now we will use the provided unit impulses and we will construct the signals. So the code here performs a convolution operation between three given signals x1 of n, x2 of n, and x3 of n, and a unit impulse sequence delta of n. So here the range is from -20 to 20, and the impulse here, the impulse creates the unit impulse sequence where the value is 1 at n is equals to 0 and 0 elsewhere. x1, x2 and x3 are the three given signals. Here, y1 is the result of the convolution that is performed between x1 and delta n. y2 is the result of the convolution between x2 and delta n, and y3 is the result of the convolution between x3 and delta n. And the option same in the convolution function ensures that the output signal has the same length as the input signal. And then we just plotted the signal. So if we run the code, we will observe that the graph here displays the convolution results for each signal convolved with the unit impulse sequence, and the convolution operation represents the output of a linear time invariant system when the input is the respective signal. It essentially captures how the system responds to the given input signals. Number 5. Splitting a signal into even and odd parts. The provided code snippet splits the given signal into its even and odd components, for which we will have to make a function with the name even and odd. Here we made the function with the name even and odd. X is the input signal and n is the corresponding time indices of the signal. X of E is the even part of the signal, X of O is the odd part of the signal, and M is the time indices of the resulting even and odd parts. So the functionality of the code is that the function first checks if the input signal X is real. If the signal contains any imaginary component, that is imaginary of X is approximately equals to 0, it raises an error. It then determines the time indices M to cover the range for both N and its flip version, which is here. Then it aligns the input signal X with newly determined time indices M to ensure proper alignment for further operation. The even part xe of the signal is computed as the sum of original signal and its flip version divided by 2. Whereas for the odd part xo, the signal is computed as the difference between the original signal and the flip version divided by 2. The formulas are given here for the even and odd parts. The code that we were provided in the manual. Uh, in this code, X is the given signal and defines the time indices for the signal ranging from 0 to the length of the signal minus 1. For even and odd signal splitting function, xe xom is equals to even odd function. We use the even odd function that we made here. Its functionality will be used in this code. And then we simply plotted the function. So when we run this code, we will observe three subplots. The first one is the original signal, second one is of the even signal, and third one is of the odd signal. Task number 6. Impulse train can be used for sampling of continuous time signal. Use following continuous time sequence. We have been given the code snippet and we have been asked to make some logic to discretize the above given sequence. So in this given signal demonstrates the comparison between a continuous time signal and its discrete time counterpart, which is obtained by sampling the continuous time signal. Here T underscore continuous defines the time axis for the continuous time signal from 0 to 2 seconds with a step size of 0.005 seconds, resulting in a high resolution representation of the signal. Fn demonstrates the frequency of the cosine wave. Ct underscore signal, which means continuous time signal, is cos of f2 pi into 2 into t continuous, which computes the continuous time signal as a cosine wave with the frequency f. The continuous time signal is plotted in the first subplot. For the discrete time signal, which is sampled, fs is equals to 40, which is the sampling frequency. T is equals to 1 by fs, it is the sampling period in seconds. T underscore discrete is the time axis for the discrete time signal by sampling the continuous time signal at the interval of Ts from 0 to 2 seconds. Dt underscore signal is basically discrete time signal, which computes the which computes the signal by sampling the continuous time signal at the specific time points. So, and then we simply plotted the graph. So when we run this code, we will observe a graph like this. You see in the first subplot, it is of continuous time signal, and in the continuous time signal plot, you see that the cosine wave appears smooth and continuous because of because it is represented with a high resolution time axis. Whereas when you see the discrete time signal, which is the sampled signal, the cosine wave is represented by individual samples taken at specific time points, and the stem plot displays the discrete points indicated the samples of the signal. So this comparison illustrates that the concept of sampling in signal processing, where a continuous time signal is converted into a discrete time signal by taking samples at regular intervals.